Assalamu alaikum. Today we are going to discuss two topics from the practical optimization book, the necessary and sufficient conditions for local minima and maxima. And the other topic is classification of stationary points. Those are basically article 2.5 and 2.6. So most of the content of these two articles are already covered from some online videos as well as from the earlier classes. So that is why instead of covering this topic in the class uh, and utilize the time for something more useful, we better cover these topics in the slides. Okay, so now the first topic, necessary and the sufficient conditions for local minima and the maxima. We have seen that already the gradient g of x and Hazen matrix h of x must satisfy certain conditions for a particular point to be a local minimizer. So there's two sets of conditions basically have been discussed in this book. The first condition that must be satisfied at a local minimizer. This is what is called necessary condition. And the other one is the condition that guarantees that that particular point x star will be a local minimizer. That is called basically a sufficient condition. So one is the necessary condition, and the other one is sufficient condition. So the necessary and the sufficient condition can be described in terms of number of theorems, a concept that is used extensively in these theorems is the concept of the feasible direction. So this is something new. In a lot of books, they actually use this one. So we have seen that in the Taylor series, what we have done is around any particular point. So what we have used is a small perturbation. So if it is a critical point, that is x star, and then x star with, in some book we have used sigma, in some book we have used delta, and in some books we have used H as well. So these are small perturbations basically around or in the neighborhood of the X star, or small vicinity around the critical point. So basically here, this epsilon del or H is being actually replaced by some directions and some magnitude. So directional, so this del is being replaced by alpha D, where D is actually a direction, feasible direction map. So that perturbation that we're talking about, small perturbation, that is within the feasible range, within the feasible region R, it has to be in the feasible region R, where that small perturbation is basically given by a directional variable. Okay, so directional perturbation. And where your alpha is within bounded by 0 and alpha hat. Since we are interested about a small point, so we generally take it as a 1. Okay, so let's see a few example whether basically more or less practically what we are going to do is that directional vector will be in the opposite direction to the gradient. So gradient, we generally say that the growth, but since we are trying to minimize the problem, so it will be actually opposite to the growth. So it has to be a certain direction that follows the minimization of the objective function. So let us see how can we actually define the directional feasible direction variable, that is your D, with some example. Okay, so Example 2.2, the feasible region in the optimization in an optimization problem is given by R, where R is the set of X, where X1 is greater or equal to 2 and X2 is greater or equal to 0. So that means X1 is greater or equal to 2 and X2 is only positive, all positive values, including 0. So our first objective is to actually plot this. So in this axis, we mark, so this is our origin. So we mark 2 and X2 value has to be greater. So this is the feasible zone for X2 and X1 is only positive. So basically this area is our feasible zone or feasible region. Okay, so this is our R. Now we are given few direction. Direction is nothing but basically the vectors. So D1 is -2 and 2. D2 is 0 and 2. And D3 is 2, 0. Okay, so we just figure out those points in the graph. So -2, 2 here is one direction. So this is one D1. Then you have 0, -2. So X value 0, X1 value 0, and X2 value is 2. So this is our D2. And 2, 0. So X1 value is 2 and X2 value is 0. So this is another direction. So 3 directions are given. And we are asked to figure out whether, and 3 point is also given, X1, X2, and X3. So what you have to do is whether these directions are feasible for these points or not. Okay, this is what you have to figure out. So find out, our next target is to figure out the points. So X1 is basically 4, 1. So this is where we have it. Then X2 is 2 minus 3, 2, 3. This is, here it is. And X3 is 1, 4. Now we have to see whether in these points, the direction vectors that has been given, whether they're feasible or not. So in the X1 point, as you can see, the direction D will be something like this. And X1, the direction D2 will be something like this, going up. And the direction D3 will be something like this. And as we said, that alpha hat can be 1, as it has been assumed here. So for any value in between 0 to 1, so all 3 direction D1, D2, and D3 is actually feasible for X1 points. Whatever the direction you take, still we are within that bounded region or our feasible region. So you can say that all 3 are basically feasible direction for X1. Now for X2, so X2 is actually here. So X2, D1, if you take a direction D1, then you can see we are actually leaving the surface, leaving the feasible region. So D1 is not a feasible direction for the point 2. So it's not. Similarly, the other 2, so D2 is still, because our X2 is basically can have a value 2. So this is a feasible direction, as well as this one is no doubt about this one. So for the second case, D2 and D3 are feasible, which has been shown here. And what about X3? It itself is outside the feasible zone. So any direction, whatever the direction you apply, this definitely is going to be not the scenario, D1 and D2. But there may be a doubt that whether the D3 with a higher value of alpha, whether that will be feasible or not. But as I said, that we are actually considering a small perturbation around the critical points or around any point. So that alpha has to be smaller. So somewhere here. So that is why all three, D1, D2, and D3 is considered to be not feasible because the point itself is not feasible. Okay, so this is direction is been included while we are trying to apply the formula, like also in the Taylor series expansion. So we want to include the directional perturbation instead of a small perturbation of omnidirection, maybe or any arbitrary direction. Instead of that, we try to apply with a directional perturbation. So this thing seems interesting, and also I think most of the modern papers or modern books, they follow that. So that is why we also should try to use these notations. Now, once we have gone through that one, now start with a few theorems. Those are actually known as first and the second order conditions, basically including the first and the second order derivatives of our Taylor series expansion around the critical point x star. Critical point is also known as stationary points. Okay, so let's start with the first theorem. The first theorem is the first order necessary condition for a minimum, and it says that the function fx, if it is continuously, if you can have a continuous derivative of fx in C1 plane, then the condition for x star to be a local minimizer is the gradient, the directional gradient has to be greater or equal to 0. So this is a necessary condition. And if x star is located interior to R, that means if x star is inside the feasible region R, in that case, the gradient has to be strictly 0. So if it is interior, then your gradient of x star has to be basically 0. So the proof is somehow mathematical and understandable, of course, but we believe that we can give more focus on solving the problem than the derivation itself. Knowing the theorem is good enough, and if it is better if you can try to comprehend this one. So that is also good, but it's not necessary that we have to somehow try to understand the whole thing. Okay, so now what it says is that we are assuming that our x is having a small perturbation, directional perturbation around the critical point x star. Okay, and the condition also says that alpha has to be bounded by alpha hat and 0. So the Taylor series expansion says the value around the point x star is the value itself and a gradient of them. Then you have the higher order terms. In this book, they are called remainder, okay, or higher order term, HOT. So the gradient value, since our condition says that it has to be greater or equal, so we just assume the opposite one first, that we are assuming that is smaller. And if we assume it to be smaller, and as alpha goes high, the higher order term is even smaller. So we can say that this whole thing, that means this portion will be smaller. And if this portion is smaller, then we can say that fx minus fx star should also be smaller than 0. So it's justified that fx has to be smaller than fx star. But we have said that the point x star has to be a minimum point, isn't it? So this is a clear contradiction. So that is why the gradient of gradient of x star t cannot be smaller than 0. So rather, it has to be greater or equal to 0. So this is a reverse way. By contradiction, we try to prove it. Okay, so now, okay, so now necessary and the sufficient conditions for the local minima, the theorem, with the second part that I've said that if it is interior, then it has to be 0. Why we're saying that if it is interior, and the point is interior to the region. So this is what we'll try to say. If it is inside, then if you take this direction or in the reverse direction, since they are vector, the magnitude has to be reverse. So in one direction, if it is plus, in the other direction, it has to be minus, but we know that there has to be following the same rule. So in the same point, it cannot be plus or minus. So that is why it has to be 0 if it is interior. If the point x star is interior to your feasible region R. Okay, so that is why. So if you take one direction in this way and the other direction in this way, so their magnitude is supposed to be reverse, but which cannot be true because in all cases it has to be greater than or equal to. So since they are having opposite sign, it's better to take it as a 0 when the point is interior to interior of the flexible region R. Okay, so next is the second order necessary condition. For second order necessary condition, we have to define the quadratic form. We already used in some of the cases previously as well, but not maybe in terms of D, rather in terms of some other variable like del transpose Hn, the del transpose. Somehow the pain is not okay. So this is what we have used previously. Now, since we are using the directional perturbation instead of del, so we can use redefine that thing. And also in one of the classes we have shown that this matrix or this quantity, which is a quadratic quantity, will be positive, definite, positive, semi-definite, negative, semi-definite, or negative definite based on the values of the Hessian matrix actually. Is it okay? So that condition has to be satisfied. So now, and also the converse one is also true. So if that matrix is already semi-definite, then your Hessian matrix has to be also positive, definite, semi-definite, correspondingly, basically. So this is nothing but your function. So the function being scalar quantity, we know that its value has to be, since it has been defined by the Hessian matrix, it has to be greater than the conditions, will be corresponding conditions has to be fulfilled as given here. Okay, now the second theorem, the second order necessary condition for the minimum. So now our function fx has to be continuously differentiable, second order differentiable. So x star is a local minimizer with the feasible direction D at x star if this is necessary condition, not sufficient condition. So according to the necessary condition, it has to be greater or equal to the first order. The gradient has to be greater or equal to 0. Okay, and if gradient is 0, then goes to the second condition, and in that case, our the quadratic equation has to be greater or equal to 0. So this is not certain. This doesn't guarantee. That is why it is necessary condition. Whenever it guarantees, then it called sufficient condition. And similarly, you can also prove that if x star, if it is interior of R, then the value gradient always has to be 0. So let's try to see the proof again. The proof are not that necessary. Comprehension is more important, but still it's better to see how it's working. Okay, so the proof has been actually shown in the similar way. This time what has been done is the Taylor series has been expanded to second order with Haitian. Then you have additional higher order terms. Eventually what we are going to say that we are going to avoid that. Okay, so this gradient is going to be vanished because of the fact that we have assumed that it's equal or greater than 0. So what is left is these two parameters. And again, since we are saying that that has to be greater for the second one, that has to be greater. So that is why we just greater or equal. So that is why we again take the reverse one, that is negative. And with the negative, we can show that the whole term is becoming negative. So fx is becoming smaller than fx star, which again contradicts, because our point of concern is x star, and that has to be a minimum. And from that, we can say that if gradient is 0, because if the gradient is not 0, then we cannot conclude and go to the next condition. So if the gradient is 0, then it has to be greater or equal. The Haitian or the quadratic matrix has to be greater or equal. So this is how we can get our necessary condition of the second order. So now let's look at these two problems with directional perturbation as well. So example 2.3, as well as we are going to see example 2.4. So example 2.3, as you can see, the point x star is given. So our x star is basically half and 0. And the minimization function is fx given here, and subjected to the inequalities that x1 and x2 both has to be greater than 0. So we know that, and our objective is to show that the necessary conditions fulfill in our case. So we are just figuring out the and somehow it may make you a bit confused, but don't get confused. Actually, this is only a notation. What does it mean is del f by del x1 and del f by del x2. And then you have your D matrix, which is D1 and D2. So now if you cross multiply, if you just multiply these two, then you are going to get something like this: df by dx1 d1 plus df by dx2 d2, which is nothing but the second term of your Taylor series expansion. So we already figured out these two. Then with the first one, we multiply D1, with the second one, we multiply D2. Then you can see after a bit of simplification and applying the condition that is a half and 0, that means x1 value, x1 star is half and x2 star is 0. So if you plug it here, okay, so x2 is getting vanished. And this one is, if you give half, then it becomes 1 minus 1. So the first term is getting vanished. In the second term, 1 plus half. So basically 3 by 2 d2. So we know that the first sufficient condition says that the gradient has to be greater or equal. Okay, so greater or equal to 0. So and if it is only true when our d2 is greater or equal to. So this is one of the condition to be fulfilled, that d2 has to be greater or equal to 0. Now, for the going for the second order condition, we have to start with this condition has to be 0. Now, if it is 0, okay, then we can calculate our Haitian matrix. That is nothing but your del square f by del x square, del f del square by del x1, del x2, it has to be 1. Same here, del x square f by del x1, del x2, and del square f by del x2 squared. So you figure it out, then plug the values here. And what is this? And how this is coming is simple. We already done that. So D1, D2, which is D transpose. Then you have Hessian matrix 0, 1, 1, 0. Okay. And then you have D1 and D2. So now if you multiply, you're going to, so that this will be the coefficient of D1 square, this will be the coefficient of D2 square, and these two will be added together to form your D1 and D2. So this is how it is coming, and we know that we assume that because for the second order, the gradient has to be 0. The gradient is a function of actually your D2, so D2 has to be 0. So if you apply D2 equal to 0 here, so only the thing left is this one. And we know that necessary condition is the value has to be greater or equal to 0. That means our condition will be D has to be greater or equal to 0. So if it is fulfilled, then we can say that both the condition is actually necessary conditions are actually satisfied for a minimum. So this is how we can show with the directional perturbation how to figure out whether our points, whether any particular point will be a minimum or not, based on actually this necessary condition. But it doesn't guarantee. It just these conditions are necessary, but to ensure this, actually we have to go for the next condition. Okay, so now with this particular problem, as you can see, there's 2 points given, P1 and P2, and a function is given subjected to the conditions, inequalities that x1 and x2 both has to be positive. So again, similar thing you have to do. Basically, gradient thing you have to figure out, and you have to set the gradient with your directional variable, similar way. Then for second order condition, basically the gradient has to be 0. You know, if you put the 0 here, then you plug the value, figure out the value of the Hessian matrix in terms of the parameter x1 and x2, and then put the first point P1. And you can see that your Hessian is becoming 0, 0 at point P1. So H P1. Now you just give your directional variables with that one. So D1, D2 with your Hessian matrix with D1 and D2. The first one is the transpose, the second one is actually D1, D2, and then you cross multiply. You're going to see that it will give you 4 D2 square. So it can be a local minimum if your D2 is greater than 0. Okay, the second case at point P2, somehow it's been cut, but if you look at that one and apply the similar kind of thing that you're going to get at point P2, you have a function like this. Now you have two terms are positive and one term is negative. Now if you take both of them one, as you can see that 18 and 4 is basically 22 and it is minus 24. So your result will be minus 2. Now if you take any other values of D1, say D1 is or D1 equal to 0, any one of them is 0, then as you can see, this result is coming from both of them 1. And now say 0 and 1. So if you take 0 and 1, so this term is becoming 0, this term is becoming 0, so your value is becoming plus. So you will have 4. So now sometimes it's giving you a plus result and sometimes a minus result. So positive values also coming, negative values is also coming. This is this means that your your function here is actually indefinite. It takes both the values. So our point P2 violates the condition. So basically, it cannot be a positive or it cannot be a maximum or minimum. So it will be rather a saddle point. So next, try to see. Okay, so the necessary and the sufficient condition for local minimum. So now the theorem, the 2.3. So this is necessary condition for a maximum. Actually, there's a reverse one. So we are not going to cover that thing in detail. We are actually just generalizing the minimizer. So you just have a look at that one. Now we want to go for the sufficient condition for a minimum. So again, for the sufficient condition, your fx is differentiable, second order differentiable, and your x star is located interior to R. And in that case, your condition will be the gradient has to be 0, and your Hazen has to be positive definite. So the Hazen matrix at 8x star has to be greater than 0. And if these two conditions true, this gives you certainty, and that is why it is also known as strong local minimizer, the point x star. So proof is also given. You can go for that one as well. So similarly, second order scenario. Now, if you can see here, these are the two values we get, and if this is strictly positive, how can we know this is strictly positive? Because of the your directional variables, they're actually coming as a square, as a norm of 2. So they are actually always positive. So only depending on the value of h, we are determining the values of our function. So if this is greater than 0, then definitely our value of the f d with the perturbation has to be greater than this one. And this is the only condition that fx is a minimum point, isn't it? So that is why it's relatively easier to figure out only the Hazen, if it is Hazen matrix is greater or positive definite, it certainly gives you a stronger condition, and that makes your x star to be a strong local minimizer. Okay, and the second of the sufficient condition for a maximum, just the reverse one. So negative definite it has to be, that is the condition. Okay, so the next topic is basically the classification of the stationary points. So we know that when the gradient equal to 0 gives us the stationary points or critical points, and then we have to decide whether that point is a maximizer or a minimizer or a saddle point, so undefined. So the definition of the saddle point is given here, a point x star that is x bar is within the region, and that within the feasible region is said to be saddle point if gradient is 0 and x bar is neither a maximum or a minimizer. So basically, if you now take any arbitrary, take any feasible direction that is within the region R, and then you try to find out the perturbation, what you're going to get, and with obvious necessary condition, the gradient has to be 0. Then you're going to see that for some direction D1, the point is smaller. For some direction D2, the point is greater. So we cannot give a certainty that it is always going in a certain direction, positive or negative. So in one direction it is positive, in other direction it is negative. So, and also likewise, our Hazen matrix will be the determinant factor here. So the Hazen matrix is also giving plus values sometimes, and it's giving minus values sometimes. So it is indefinite, and that is why the point cannot be a maximizer or a minimizer, rather it has to be a saddle point. So here in a figure, we can easily see the points here. So this point is a minimum point here. Okay, and this point here is this point here is also a minimum. This is a maximum. This is a maximum. This is a maximum. But at this point, as you can see, in this direction is going down, and in this direction is going up. So in some point it is going down, and in some point it is going up. Also in this direction it is going up, and in the downwards it is going down. So basically, it doesn't give an indication of being a maximizer or a minimizer. Rather, in some direction it is positive and in some direction it is negative. This topic somehow we have covered in a generalized way. So we have said that if you have to keep differentiating, and you have to check when you have a non-zero condition. Okay, so nth derivative of the function you have to find until you have a greater than 0 for a minimi, and nth derivation has to be smaller than 0 for a maxima. Okay, so these are the conditions we said. And also we have said that if the value of n is odd, then it is a inflection point, which is also similar to your saddle point. If n is even, only then these two will give you a maximizer or a minimizer. So this topic is already covered, but the mathematical notation of this book is slightly difficult than the other lectures that we have followed in earlier. So now one example is given, example 2.5, find and classify the stationary points of the function fx. So our first objective is to find the gradient, set the gradient equal to 0. That will give us a stationary point here. X1 is 2, 3. So sometimes the transpose may confuse you, but you can always write in this way, so confusion can be avoided. So now you go for the second derivative and find out the Hessian. So this is generalized version, and as you can see that your Hessian at x is becoming 0. Okay, so if it's 0, then it means it falls to the condition that Hessian can be greater or equal to. That means it falls in the condition of the semi-definiteness. Okay, so there is a we have to do more work is necessary in order to determine the type of the stationary point. So we cannot actually conclude whether it will be a maximum or minimum, because we have said n number of derivation you have to go. So the second derivation is also 0. So we have to go for the third derivative. And after finding the third derivative, we can see that for some values of del it is positive, and for some values of del is becoming negative. So our function is neither a maximum or a minimum, rather it becomes a saddle point or inflection point. Okay, now to find out these conditions more easily, we can also have few more theorems. The theorem 2.6, the characterization of symmetrical matrix. So if you have a symmetrical matrix, the H, and that matrix is positive, definite, or positive, semi-definite, or goes on, if and only if you can have another matrix B, which is in the same dimension as your H, and you can see that your H hat is B transpose HB. So if this is true, then you can say that H transpose can also be positive definite, positive semi-definite, likewise, whatever given here. So if X can be written with a same dimensional matrix with this format, then your H hat, which is this one, is also going to be same. It will have same property. So the property of this one and the property of this one will be same. If H is positive definite, your H hat is positive definite. The H is negative definite, H hat will also be negative definite. Okay, so now if you take the identity matrix, you can easily prove that but to make it more general, they have avoided using the identity matrix. Rather, they have used some other matrix. So now, say that we have a directional vector that has been multiplied with those two. So this is what we have. Now, h hat, if you just plug in the value of the h hat here, you have two determinants, two transposes and two normal values. So B is a vector, don't get confused. B is a matrix, which is n by n matrix, and your D is actually a vector. So now, if you find out the determinant formula, we know that individual determinant, if you take individual transpose, if you take a common, so it will be reverse. So BD, the whole transpose, this should be the case. Now you can say, you can also take these two as two more vectors. So just to review, if you multiply a matrix with a vector, that will give you another vector. So we're just calling that vector as different. So we started with that condition, and we come up with another D prime with the same H. So basically, H hat and H is having same property. So if H hat is positive semi-definite, your H will also be positive semi-definite. So this is how one matrix can easily be replaced by another matrix with some similar dimension function if you have B, some non-singular value. So don't get intimidated by the term non-singular. It just refers that B is not zero. It's not a null matrix. Okay, so theorem 2, it says is characterization of a symmetrical matrix by diagonalization. So from the control system theory, we know that if you try to diagonalize a matrix, then that actually gives you the eigenvectors of that particular eigenvalues of that particular matrix will be appearing in the diagonals of the matrix. So basically, the poles are the eigenvalues. So if you try to diagonalize, and also if, then you can easily predict the values based, especially in the control system, that whether all the poles are negative or not. If all the poles are negative, your system have the pole in the right half plane, your system will be stable. So here we are more interested about the definiteness of the matrix, whether positive, negative, because we are not necessarily trying to make the system stable. Rather, we're trying to find maximum, minimum, and that depends on the definiteness of our function, of our matrix H. So the Hessian matrix we are interested about, and the Hessian matrix says that if you try to diagonalize, and if H1, H2, H3, all these values, those are appearing in the diagonal, is going to determine your the property of your matrix. So basically, if you have H hat, which is having a matrix like that, H1, sorry, this should be, element is always smaller letters. So H1, 0, 0, 0 goes on. Then 0, H2, 0, 0 goes on up to the last one will be DN, HN. Okay, so, and since we are multiplying with D transpose, H hat and D, so basically D transpose and D is going to produce D1 square, D2 square, and only the diagonal factors are available. So it will give you D1 square H1 hat. Since this is H hat, all of them has to be H hat, the element has to be H hat as well. So now D2 square H2 hat, so goes on. So as you can see, D1, these are square, positive quantities, the square terms. So only the matrix quantity depends on these parameters. So all of them positive gives your system to be positive, it makes your matrix to be positive definite. If some of them 0 and positive, then we call it them positive semi-definite. All of them is negative, then we call it negative definite. Some of them 0 and some of them negative definite, then negative semi-definite. So this is how we try to characterize the system after diagonalizing, characterize the matrix after the diagonalizing. Okay. So this is what is being shown here, and also how to make a non-diagonal matrix into a diagonal matrix. For that, this elementary transformation method is being shown here. Okay, so after multiplying with the elementary matrix like this. So basically, elementary matrix is some sort of change of an identity matrix. So if we have identity matrix, IN, with 1, 0, 0 up to 0, 1, 0 goes up to n number of cases. So you multiply one, so maybe one row with a certain value, then add with the second row or third row. So these transformations are called elementary transformation, and based on that, whatever the matrix we get, we call elementary matrix. So based on the elementary matrix, and whatever happens to the elementary matrix, it is actually reflected to your original matrix. In this case, suppose the Hazer matrix we are trying to transform. So with E1, you have to also take E1 transpose. E2, you have to take E2 transpose. E3, E3 transpose. So this combination of multiplication with of course, the first one has to be E1 and E1 transpose. It will eliminate one particular component of your non-diagonal component of your matrix. Okay, so let's see this particular scenario, and also those can also be defined by these parameters can also be defined by BT, B, and this B transpose. So eventually it becomes another transformation like this. Okay, so we know that if you have this kind of thing, then eventually they are squared up, and that makes a diagonal matrix. Okay, so a particular problem is being shown here, example 2.6. So diagonalizing the matrix. So here, what they are saying is they're adding 2 times. And how actually you determine adding 2 times? With the first row, and then we 2 times multiply the first row and add to the second row. So basically what we try to do here is we want to eliminate this component. So if you want to eliminate this component, the first row value is 1, so it has to be multiplied by 2. And if you add with this one, so 2 plus 2 minus 2 will be becoming 0. So that is why with your elementary matrix that you have 1, 0, 0, 0, 1, 0, 0, 0, 1. So what we have done is the first one will be multiplied by 2, then it will be added with the second one. So only the second one is getting changed. So first one is remaining as it is, third one is remaining as it is, second one with only these 2 will be added, multiplied with this one. So 2 will be coming here, and the rest of the thing will be. So now this is, and its transpose is this one. So this is your E1, and this is your E1 transpose. Now if you multiply these 2, E1 transpose, multiply these 2, you're going to see that this one, and because of the transpose multiplication, these 2 are actually vanishing simultaneously. Similarly, now which component you want to eliminate? Suppose we want to eliminate the 4 of this one. Okay, so this 4 we want to eliminate. So you have to add minus 4 with this one. So that is why the first one has to be first row has to be multiplied by 4. Then you have to, or minus 4. Then you have to add with this one. Then the third one will be only changing. So what we are going to get is first one will be remaining as it is, second one will be remaining as it is. So first one is minus 4, multiplied with minus 4, and add with that one. So the rest of the parameters will be. So this is your second or E2. So now if you do that, then and with the transpose of that one, with the transform matrix, this one, so that these two parameters is vanished. Similarly, to vanish 8, so what you have to do, as you can see, and that if you want to vanish the 8, then you have to multiply the second one with 4, then you have to add with this one. So the second one is multiplied and adding with this one, which is actually changing the third one only. So in the third one, you multiply with 4, so 4 is coming here. So after multiplication, it is going to give you a matrix like this. Now, as you can see, diagonal, one is positive, one is negative, another is. So either all of them has to be positive for positive definite matrix, all of them has to be negative for the negative definite matrix. For negative or positive semi-definite, you can also allow 0. But here what you can see is that some of them are positive, some are negative, so it is H is indefinite. Okay, it doesn't correspond to a positive value. Similarly, here we can only with only one component is here, which are also symmetric. So we just have to try to eliminate that one. So if you multiply with the first, if you just make it half, and there is 4 divided by 2. So if you just multiply the half, then it becomes. So only the half has been added with that one. So as you can see, in this particular case, H1 hat is 4, H2 hat is 2, and 50 H2 hat. So all of them are positive. So your matrix is also positive. Okay, so now the eigen, the classification of your stationary point, the theorem 2.8, eigen decomposition. So with the eigen decomposition, this one is also been studied in earlier cases. Basically, we are trying to take the principal minor and the leading principal minor examples that we have studied previously. So the formal definition has been given here. So I'll just ask you to go through this theory, and if the matrix H is symmetric, then these are actually Sylvester criteria. So for that one, we have to use these conditions, and if all of them are real, in that case, based on your principal, the leading principal minor, you have to decide whether they are positive definite or negative definite, and based on the principal minors, you have to decide whether they are positive semi-definite or negative semi-definite. So this is all the criteria, the summarized thing that we have covered earlier. So theorem is there, given there. We try to avoid the proof, but the proof is not that complicated. If you are interested, we can also discuss that thing in the physical class. So a few examples are given here with the leading principle. Actually, the previous two problem, 2.6 and 2.7, those metrics are given. Based on that, the leading principles are calculated. So as you can see, the leading principles are having different values. So they are actually giving us an indefinite matrix. Similarly here, all the leading the principles are actually positive. So our H is positive definite. Another example, 2.9, the function given. Similar problem we have already done. So we just get the first derivative, set the gradient equal to 0, find the stationary point, find the another derivative, second order derivative, find the Hessian matrix, and your leading principles will give you a positive definite matrix. So X1 will be a minimizer. So you can easily conclude the thing. So these are repetitions. So that is why we're going quickly. So the next one is the classification, is example 2.10 on the same topic. That is classification of the points. Basically, again, the function given, do the same procedure and figure out whether you have all of them, all of the leading principal positive or not, based on your Hessian matrix. So you can see one of them two of them are negative, they're having opposite signs. Or also by diagonalizing, you can easily see. So if you just diagonalize that one, you can see that one of the diagonal is negative. So all of them has to be positive or negative. So your function, the matrix is basically Hazel. I'm sorry, sometimes I have said function, but it's try to mean actually the matrix. Okay, see you in the physical class, inshallah. Assalamu alaikum wa rahmatullah.